Hi everyone, I'm Jacob Thompson. I'm an applications engineer on Texas Instruments brushed, stepper, and solenoid driver team. This video will walk you through using our new sensorless position control devices, including DRV8214, DRV8215, DRV8234, and DRV8235, using the new Web GUI interface. First thing you're going to do is select the EVM variant that you have on the right side of the screen. I have a DRV8234 EVM, so I'm going to select its corresponding tile. Give the GUI a few seconds to connect to the device, and then if the connection is successful, in the top left it'll display that the connected EVM is your EVM. If this is the first time you're using this particular EVM with the GUI, we recommend performing a firmware update via File, Program Device. This will flash the latest firmware onto your EVM, and this also helps avoid a mismatch between the firmware that's on the EVM and the version of the GUI that you're using. After this, you can select a page of the GUI to navigate to. We're going to start with the Quick Start page. So this page is going to start with this pop-up for the faults, status, and driver control. This gives you interfaces for spinning the motor, reading the state of the faults, and adjusting a few common settings. This is a pop-up that can be opened from any screen in the GUI by expanding it with this blue rectangle on the right side. So the first thing you need to do to interact at all with our driver is to turn it on. You do that by toggling the end sleep pin by enabling the motor driver in the top right here. So click this, and now all of the user interface controls are selectable and movable. From here you can select whether you're doing phase enable mode or PWM control, or speed regulation or voltage regulation. You can read the status of the faults. You can adjust a few other common settings such as the PWM frequency, VREF, S mode, I mode, etc. So in order to start spinning a motor, we're going to enable the outputs. We're going to click Start Drive, and then we will adjust the in1 duty cycle from 0 to 100. The ramp rate on the right will be applied to the input signal to slowly ramp the device up or down to your desired target duty cycle. You can adjust this to a lower value for a faster ramp. 0 is effectively no ramp at all, and then or a maximum ramp of 25, which will correspond to a few seconds to start spinning the motor. To stop the motor, you can click Stop Drive, and then note that a lot of things are grayed out right now. This family of devices has certain registers that can only be modified if the outputs are disabled, which you should see in some of the tooltips. It needs the enable out bit to be 0. In order to edit these things, simply go to the top right and disable the outputs. Now we can once again select between phase enable mode, PWM mode, and other device controls. So after that, let's go ahead and close this pop-up, and now we'll start walking through the ripple counting setup, where we will set up the device for our particular brushed DC motor that's attached to the EVM. The first thing we're going to do is input the motor resistance. There are a few different ways to measure the motor resistance, and you can see these different methods by clicking this How to Measure Motor Resistance box, and then it'll show a few different methods. So the first method that's the best is to get the data from the motor datasheet if it's provided. However, many brushed DC motor datasheets don't provide the resistance. So then the second best method is this method 2 here. Basically, you connect a voltage directly to the motor that is a slightly lower value than where the motor will start spinning, and then read the current using a multimeter or an inline probe, and then do this for a few different voltage levels, and then calculate the resistance using V equals IR over each of these levels, and then kind of find the consistent motor resistance value. You can also do this at higher voltages by manually stalling the motor. The idea is to take the resistance measurement at stall condition, which can either be at the operating voltage of the motor or at a very low voltage where the motor isn't spinning. So I followed this method 2 for our motor that's connected and found that it's 8.35 ohms. So we're going to input that into the input box, and then you'll see that there are some suggested values that are populated on the right. Go ahead and select those on the left, and this will apply these values to the register in the device. It suggests a motor resistance inverse scale of 1024 and a motor resistance inverse value of 122.6, so we'll put in 123. If you are using a DRV8214 or 8215, you would be able to adjust the CS gain select for your device. You would select a value of the peak current that is as close to the peak current of your motor while being higher than it. So if your motor could draw 0.8 amps, you would pick the 1 amp peak current setting. DRV8234 and 8235 do not have this setting. Now for step 2, we will need to connect the motor and start the motor spinning using the driver control pane. So let's go ahead and do that. Expand the driver control pane, enable the outputs, click Start Drive, make sure you have an appropriate ramp rate so that you don't trip overcurrent protection, and then go ahead and start spinning your motor. My motor is now spinning. So this step is going to have us take an oscilloscope capture of iProppy output over 50 milliseconds and then manually count the number of peaks. You can click here to see an example. See, this is a scope capture of the iProppy output signal from the device, and then the pink section is 50 milliseconds long. We're going to count the peaks. If you want, you can do more or less time for more accurate, but we recommend counting at least 20 peaks to have an accurate measurement for this. So we can pull up our oscilloscope and see that our motor is spinning and that the RC outs are very not matching up with the current setting. So we're going to go ahead and take a capture, zoom out and select 50 milliseconds. So here we are at 50, and then you would go in and count the peaks. 1, 2, 3, 4, 5, 6, etc. Ours happens to be 30 peaks. So from here, we go in and say we had 30 peaks or 30 ripples over the course of 50 milliseconds. So then this mean current ripple frequency box is going to update with this is the target value that we're trying to tune our motor driver in to reading. So 600 hertz, our device actually is using units of radians a second. So we want a value around 3,769 radians a second to be reported by the device as the ripple speed. So it's already spinning, and so these suggested values will be constantly updated as this ripple speed value is updated. All you have to do is click Update, and then those values will apply to the device. Then just wait a few seconds for the device to be able to update the ripple speed, and then these suggested values will also be updated. Sometimes if the number maxes out, this KMC scale can get basically saturated at 24 times 2 to the 13th, and this formula will get stuck and won't arrive at a value that works. So in that case, I recommend reducing the KMC scale manually, then waiting for this to update and see what it gets. Still not updating. So our device datasheet will state that you should start with the KMC at the max value to help tune in. And so here we see now that the ripple speed is not saturated, these suggested values is changing again. So now we're going to click Update, and then now it has arrived at values that are close to our target frequency. So this green checkbox will be displayed whenever it is within 2 times the ripple speed scale of the target value. So 3769 plus or minus 2 times 16, 32. It'll be yellow if it's within 4 times the ripple speed scale, and it'll be a red X if it's outside of that. So now we have successfully tuned it in. Let's open up our scope and see if our RC out matches up with the current. And as you can see, it does. Note that this RC out pin is unique to the DRV8214 and DRV8234. So with 8215 and 8235, you won't be able to use the RC out pin to visually confirm that your settings have matched up with the device. All that you'll be able to read is that this ripple speed matches the current ripple frequency. And you can see that it's bouncing around a lot, and so that's something that we'll be able to fine tune using the dashboard page with some more controls for the device. The speed and voltage regulation setup page provides a few easy ways to configure the device for speed or voltage regulation and then adjust the target speed or the target voltage. First, in order to set speed or voltage regulation, the outputs must be disabled. So simply go to the top right and toggle the outputs to disabled. Use this drop down to select speed regulation, voltage regulation, or one of the other regulation schemes. I'm going to select speed regulation. Then move on to step 2, and you can set the electrical target speed in radians a second or hertz. So let's say you wanted 1000 hertz, you can type that in here. Then this is going to automatically be converted to radians a second and then applied to the device. Register WSET_VSET. If you are in voltage regulation mode, then you would instead use the bottom box to input the target voltage, which will then set the WSET, the VSET value appropriately in the registers. Step 3, you can adjust the soft start duration in milliseconds. This will then automatically be converted and applied to the device settings. Step 4 allows you to change the PID parameters, which very few users are going to need to change. After this, you can use the driver control panel to enable the outputs and then start your motor spinning and adjust your speed regulation target and or your soft start stop settings appropriately. After this, you can click Finish to move on to the main dashboard page of the GUI, where you have controls for many settings of the devices all on one convenient page. The dashboard page has a lot of controls on it, so let's go section by section and summarize them. The top left section is about the ripple counting settings and the settings that we adjusted to tune in for our particular motor. This includes the motor resistance inverse and inverse scale, the KMC and KMC scale, the CS gain select if you're using a 8214 or 8215, and the error correction option. The top right box are the advanced functions. You can access these by toggling this toggle to enable all of them. Here you can adjust the KP and KI. You can adjust the numerator and the divisor of this number, and then the bottom will give you the real KP value that's going to be applied to the device. You can adjust the filter input scaling factor, damping constant, cutoff frequency, response time, and voltage filtering method. These each have a recommended value in their drop-down list. So you can see for filter input scaling factor, we recommend a value of 16. The bottom left quadrant is applicable to DRV8214 and DRV8215. This allows you to set a ripple counting threshold for the device to run to and a corresponding threshold scale. And then the device will read out the ripple count from the device. You can adjust the end-fault response, whether end-fault is going to be asserted whenever the RC count reaches the threshold, or if it's not going to be asserted. And you can select the H-bridge response, whether the device is going to stay enabled on the outputs or disable the outputs. This bottom left quadrant is applicable to DRV8214 or DRV8234 that have the ripple counting function. This allows you to select a ripple count threshold for the device to run to and a corresponding threshold scale. It displays the ripple count read from the device, and you can select the end-fault response and H-bridge response for once the device counts the number of ripples up to your given threshold. So to give an example for this column, let's go ahead and set a threshold of, let's say, 100 ripples. You can see the threshold scale is automatically applied so that I can't select 100 because 100 is not divisible by 8. I can select 96 or 104. And then we are going to let the H-bridge be disabled whenever RC threshold hits the ripple count. And then we're going to leave the end fault as not asserted. So what this should do is we'll start our motor spinning, and then we will click clear count, and then the motor will spin for 104 ripples and automatically stop itself. We can test this by going to the driver control dashboard, clicking start drive to start our motor spinning or to enable the outputs, and then set the duty cycle to 100%. Now note that our motor isn't going to start spinning yet because our ripple count threshold has already been surpassed. In order to start the motor spinning, we will have to click clear count. I'm going to go ahead and start our oscilloscope capturing it so that we can see both things happen at the same time. So we're going to go here, and then we're going to click clear count. Here, then we can see the captured data where our motor spun for 100 ripples and then stopped. So we can do it again by clicking clear count, and our threshold was set to 0, motor spun and started. There's also a chart that will display the ripples as they go, so we can change our scale a little bit higher and then try and display 10,000 ripples, click clear count, and then as the motor spins, this chart will be updated with a line for where the most recent reading of the ripple count was. And you can see it read out in this display as well as the ripple count increases. And then once it hits 10,000, our motor stops spinning because we set the H-bridge response to be the H-bridge is disabled once the RC threshold is further than, once the ripple count exceeds the ripple count threshold. The bottom right quadrant is useful for speed and voltage control testing. Here you can see the driver outputs for several registers, such as the speed register, V out, V motor, I motor, duty cycle, ripple speed. Many of these will only be applicable if in the voltage regulation or current regulation mode, speed regulation mode. Then you have driver inputs, such as the target speed and target voltage, which will be enabled if you are in speed regulation or voltage regulation mode, whether you're using soft start and soft stop, the duration of soft start or soft stop, and the ripple speed scale. There's also a chart of, as the motor spins, the detected ripple speed, or if you scroll down, the detected voltage of the motor, the V motor. Lastly, the register map page can be accessed on the left by clicking the pencil icon. This provides access to all of the registers on the device. You can select a given register, and then the right side will show you each of the items within that register. If it's something that you can configure, it'll have interactive drop-downs and checkboxes for the items that you can adjust, such as change the in out function. And then you'll see that some items might be locked in here, even though they aren't reserved. You can change those by making sure the enable outputs is set to disabled, because some items can only be changed in this device if the outputs are disabled, such as VM gain select or vsense select. So here they're locked, then we can change outputs to be disabled. Now we can adjust these values, and then once we do enable it, their value will be kept to whatever we adjusted it to. This has been a video walkthrough for our new sensorless position control, speed and voltage regulation, and ripple counting devices such as DRV8214 EVM, DRV8234, 8215, and DRV8235. Thank you for watching, and feel free to order an EVM to go ahead and start your own testing with these devices.